Well, this last answer can't be topped. And I wish that many of our granting agencies and review panels would see life sciences similar. We don't know precisely, but we have some hunch. So the next speaker is Sheperd Doeleman. He's an astrophysicist at the Harvard Smithsonian Center for Astrophysics and a project co-leader at Harvard Black Hole Initiative. This is not the budget office. He is also the director of the Event Horizon Telescope Collaboration, which is the global astronomy experiment that this year won front-page headlines and the Breakthrough Prize in Fundamental Physics for producing the first ever photograph of a black hole. And I'm sure many of you have seen it in the newspapers. It's a difference between the different disciplines, right? Imagine, as a life scientist, we got a picture of something and we were trying to publish it. What would the reviewers say? Well, show us the same for a few more galaxies if you want to prove some generality. And then, by the way, we also would like to see a picture from the back of it. And maybe picture number 57 shows something different. So, with this, I would like to call Sheperd to the stage. His title is The Next Generation EHD, Making Black Hole Movies in the Coming Decades. So no longer still pictures, it's going to be movie time.
Thank you.
Welcome.
So thanks for that very wonderful introduction. We're certainly looking forward all the time. I want to talk to you about this project, a Next Generation EHD. But first, I want to take you on a little tour of the EHT itself. The whole idea of the Event Horizon Telescope is that we might hope to see a black hole. And at first we thought it was a possibility, and then we thought maybe it was a probability, and now we know it's a reality. And so taking you through this whole process will give us a springboard on which we can jump to the future. But this began with a dream, trying to see if we could see something that captures light. It struggles with all its might not to be seen. And we thought that even though there's an event horizon around a black hole which swallows light, if we could image the light that comes from gas around just the edge of the black hole, just before it goes interior to the event horizon, then we could test Einstein's theory of general relativity at that boundary where it had never been tested before. And we could also use these black holes in the centers of galaxies as laboratories. So I'll start off by showing you this very interesting galaxy. This is Hercules A. It looks very interesting. It's optical light coming from this wispy cluster of stars in the center. And it's a beautiful image, but it's not iconic. This is an iconic image because this shows you what you see when you look in the radio. And when you put on your radio goggles, you see jets of material shooting from the interior of this galaxy, spanning 1.5 million light years across. Okay, so what is driving this outflow? This outflow contains an energy equivalent to 20 billion suns exploding, 20 billion supernovae. So it's either some mystical force in there, or most probably it's a spinning black hole that's accreting matter onto it with great efficiency, launching these light speed jets that pierce the entire galaxy. And the whole goal of the Event Horizon Telescope is to peer into the interior here and magnify it so we can see the edge of the black hole. Now, in 1979, JeanPierre luminaire, kind of a visionary in simulating these kinds of systems, said, well, here's what we should see. We should see a shadow. And you can see that he ray traced all of the paths from the accreting flow in a pancake around the black hole. Some of them come up over the top. Some of them come up from below. It's never a good idea to try to hide behind a black hole. It's not a good hide-and-seek obstacle. And you wind up getting this shadow feature, this dark region interior to this disk through the lensing. And if you go back to Einstein's theory and Schwarzschild's solutions, you find out that the diameter of that is the square root of 27 times a handful of fundamental constants. Well, how cool is that? Because if we could image this, then either we could calculate the square root of 27, which I don't recommend is the best way to calculate the square root of 27, and we could measure Einstein's validity at this black hole boundary. And then JeanPierre, not content to just sketch that out, made a computer model of what it might look like in animation. And the thin line you see interior to that dark region is the last orbit of photons around the black hole. And that's really our goal, to measure that so we can find out exactly how light moves around the black hole. This, by the way, was done by hand on Canson negative photographic paper. In a pointillist fashion, he put on little dots of India ink to make this image. Now, to get an idea of what we're after, look at the way light bends around this black hole. This is the geometry of the silhouette, or the shadow. And you can see that some light rays are bent mildly, but some do loop-de-loops around the black hole. And as you illuminate it more and more with the hot gas that surrounds the black hole, most of the rays come from behind. And if you think of our Earth as being on the screen, very, very far away, you'll see that all of those rays start to trace out something that's very clear. It's this shadow, and its size is the square root of 27 times the Schwarzschild radii. So this is how it comes about, and this is really what we're after. Now, this is the best idea we have, prior to April 10th, of what a black hole might look like. This is a supercomputer simulation. It's run for many, many hours on a cluster of CPUs, and it shows that circular region. That circle is the shadow of the photon orbit. And you see more than that, you see the hot gas circularizing around. So you see this is a very complex system. So when we observe this, we're going to see some messy astrophysics, along with some very clean, beautiful, mathematically pure GR formalism. And what we had hoped to see was something a little bit like this, so we could merge the best of simulations with what we know from observations. Now, how do we do this? Well, it turns out that if you want to look at light coming from the edge of the black hole, there's only about one wavelength of light that can traverse the hot gas just about to go into the event horizon, all the way through that galaxy, through the intergalactic medium, and then through our Earth's atmosphere to our telescopes. And that's 1 millimeter wavelength. And if you go through the math, then you need to build a telescope as large as the Earth. We need to be able to resolve a newspaper being read in Los Angeles if you're standing in Boston, or some kind of citrus fruit on the moon, your pick. It can be a tangelo, whatever. But the way we do this is with this technique called very long baseline interferometry. We have radio telescopes that faithfully record the troughs and the crests of the radio waves coming from the black hole. They're recorded with extremely good time precision by hydrogen maser clocks. These are atomic clocks that only lose about 1 second every 10 million years. They're recorded on hard disks, just like the ones you have in your computer. And then they are shipped via FedEx on 747s. There's no better bandwidth on the surface of the planet than a 747 loaded with hard disk drives. And then they're combined and aligned perfectly in time so that we get the effect of having the waves from the black hole played back simultaneously in a supercomputer. And in that way, we create a lens as large as the surface of the Earth. And that gives us the imaging fidelity and capability that we can use. But how does this really work in practice? Well, it turns out if you only had a few telescopes on the surface of the Earth, you'd have a few silvered bits on this virtual mirror. Thankfully, the Earth rotates, and so it sweeps those telescopes for us through different look angles, giving you the pattern on the right, which shows that every baseline pair, every pair of telescopes gives you one bit of information that fills in that virtual lens. And over the course of an evening, we build up enough so that we can then create the image that we're after. And this also shows that the more telescopes you have on the surface of the Earth, the better we will fill in that virtual lens, and I'll talk about that in a minute. So over about a decade, after we did some proof of concept observations that showed us there was something shadow-sized to see, we then proceeded to build bespoke systems, digital systems, and put them in all of these telescopes you see here. So from Hawaii to the South Pole, to Chile, to Arizona, to Spain, we went to all of these sites, outfitted them, and they all swiveled in April of 2017 to look at the same black hole at the same moment, precisely synchronized. And this is what we saw. There's a lot that goes into this, a lot of algorithmic work, but this is the fruit of our labor, and this is a very solid result at this point. This image looks the same over 4 consecutive days, all independently verified. It looks the same in different wave bands that we compared, and it also looks the same if you use different algorithms to tease out this structure. So we looked at this from many, many different angles. we adopted in our collaboration what I refer to as creative tension. Every time we had to make a decision, we had a 2, 3, sometimes 4 different ways of getting the same answer. Not antagonistic, but all confirming. And we didn't move ahead until all of them gave us kind of the same answer. So there wasn't a first one wins kind of scenario, but they all had to back each other up. And that allowed everybody to feel that they were contributing in a very productive way, that everyone's output would be used. This shows us that there are 6.5 billion solar masses inside the photon orbit that we expect for that mass. This is extraordinary confirmation of Einstein's theory of gravity at the very edge of a black hole. This is the best evidence that we know of for the existence of supermassive black holes. And more than that, the increased intensity on the bottom shows you that there is light coming towards you at near the speed of light. It's Doppler boosted because it's moving so fast towards us. On the top, the reduced intensity is because that same gas is moving away from us at near the speed of light. And this gives you this asymmetry that shows you the rotation axis of the black hole. So for the first time also, we know at the interior of a galaxy 55 million light years away, how the black hole is oriented to launch those jets that I showed you at the very beginning. And this also puts on solid footing 2 decades of computer simulations and the best physics that we have that we used previously to simulate what these black holes could look like. And now we know that we're on the right track, and we can use this really as a laboratory to study the microphysics of what's happening around the black hole. Now, to put this further in perspective, there's no greater glory for a nerd than to get an Xkcd comic, and this is what we got. So this puts in perspective how big this black hole is. Our entire solar system fits inside of it. Pluto is no longer a planet, but I use it as a nice marker. And then Voyager 1 is the farthest from the Earth person-made object. And so this shows you the size that we're looking at. And it makes us feel tiny, frankly. So what are we doing in the future? So the next thing we're up to is what we call the next generation EHD. And we've recently gotten some funding from the National Science Foundation to begin exploratory thinking about what this would look like. And the answer, as in real estate, is location, location, location. It turns out if you start putting telescopes precisely where you'd like them, instead of going to where the telescopes happen to be, which is what we did previously, you can engineer an imaging array that can bring black holes much more sharply into focus. So you can see here all the blue lines are those that we hope to start to energize over the coming decade. And if you do that, then the idea is that this is going to be transformative in a number of different directions. This is my only text-heavy slide in the entire talk. But in phase 1, we're going to design out for the next 3 or 4 years, and then phase 2, there'll be a build-out, many new stations. And because we have some very big stations already, we can use small telescopes and nimbly put them in the best locations. We're going to expand our bandwidth by a factor of 4. So thanks to the gaming industry and the internet, we're riding the coattails of Moore's Law. And this is really what has allowed us to build the Event Horizon Telescope in the first place, and it's what will allow us to build it for the next generation. Dual band observing, instead of observing at 1 frequency, we'll observe at multiple frequencies. Our data volume's already staggering, 10 petabytes. We'll jump up to 100 petabytes. And I think even for some Google executives, that gives them kind of the shivers. And more than that, we have to process that data. We have to transport that data and process it. So we're looking at new ways of free space optical data transmission from the South Pole, for example, high-speed internet from remote sites. We want to process on the cloud. And we want to optimize everything. And we think that we can make the move, and this is important, from still images to making movies to answer fundamental physics questions. So that baseline plot I showed you before, that virtual image I showed you before, everything in there was the black points you see. If we add the new sites, we get the red points. And if we add the second frequency, then we get all the blue points. So it's a dramatic expansion in this virtual lens that we can assemble. And if we can do this, then we start to get to some really interesting astronomy and physics. So on the left hand, you see the black hole simulation, but you also see its connection to the jet, how it launches that high-speed jet that can pierce the galaxy. Now, in the middle, you see how we could recoup all that intensity with the current array. And you can't make heads or tails of the faint emission that's the key to understanding how that jet is launched on the left. But with the next generation EHD, we'll be able to faithfully reproduce all of the bumps and wiggles, all of the corrugations, all of the instabilities and turbulence in that jet flow. And we'll be able to study how jets are launched from supermassive black holes. We can also start to make movies. So if we put enough telescopes around the surface of the Earth, we can begin to make animated recreations of what we're seeing. Now, this is work being done. I want to say also, this is work being done by many people in the Event Horizon Telescope team. The prior simulation was done by Andrew Shale, who used to be a graduate student in our group and is now at Princeton. This work is being done by Michael Johnson, Katie Bauman, and others. And you can see on the top, we can begin to make some movies with what we have now. But on the bottom, if we have many more stations and use dynamic regularizers, which is a new algorithm, we can begin to track the motion of all that hot gas around the black hole. And that's important because up till now we've been testing Einstein with light bending, but now we can test Einstein with the motion of gas around the black hole, a completely different test of Einstein, because that will give us the period. We'll be able to time the orbits of things around the black hole. To put this in perspective, we have a 4 million solar mass black hole in the center of our galaxy, and it takes half an hour for matter to orbit that black hole. Okay, so it is moving around at very close to the speed of light, and during one night of observing, you see many orbits, like the heartbeat of the galactic center moving around, and that's what we're after. We can look at real-time movies just with models. So you see here on the left a schematic model with just a hot spot created by, let's say, magnetic fields recombining and heating the electrons in the flow that's accreting on the black hole moving around. Currently, we can begin maybe to see that. On the right-hand side shows you what we can do now. In the future, though, we think we'll be able to make much better movies and model that to get the periods and just read them off like a strip chart recorder. And then we, of course, want to go into space. We don't want to be limited by the dimensions of our planet. I mean, who does, really? And on the left, you can see the slow Earth moving, and you can see how slowly that virtual aperture fills up. And on the right, in the same amount of time, we have virtually filled the aperture plane. This looks like Alex's talk all of a sudden. You know, we're bouncing billiards all around the interior of this circle, right? But we're filling it, so I guess we're illuminating the entire room. And this is with a low Earth orbit satellite, but we can also put some in mid-Earth orbit or geostationary orbit. But you can see now we've completely covered that aperture. We can have very, very high fidelity images from that. And then here's what we hope to do if we could put things further out into space. So in the model, you see the actual image that we're simulating with the wisps, the photon orbit being shown their lens, the shadow imprinted on it. In the middle, under EHT, you see what we might be able to do now, very slow cadence reconstructions. On the right, if we had, oops, can we go backwards? Is it possible to go back? Oh, maybe we can, oh yes, we can go back. On the EHT plus LEO, that's what we can do with a low Earth orbit satellite. And the bottom, though, if we had multiple orbits, then we could start to recreate the real movie itself. So imagine having a front row seat at one of the universe's most incredible cosmic spectacles. So as I wind up, I want to emphasize that this is the work of many people. The arc of this project has gone from a few people getting together, assuming high risk, being innovative, taking chances, but you can't do this kind of thing unless you build a global team, and that's what you see here. This is the Event Horizon Telescope collaboration in one of our meetings. We're 200 members strong, 60 institutes, 20 countries and regions represented, and this spanned the gamut from instrumental work, going up to high sites. We go to some of the most extreme spots on the globe to do this kind of extreme astrophysics. We took those instruments, deployed them, we data processed them, so we needed algorithmic work. We had to make the images. We used computer vision techniques to do that. And then we had theorists who were involved in the interpretation. So in every aspect, we took the best resources we could across the globe. And even though there are some things that divide us as people, this technique of the EHT, the very long baseline interferometric technique, nimbly sidesteps all that and allows people to work together without thinking about politics too much. And funding comes in from various funding agencies, which supports the entire endeavor. And then I wanted to say something about the impact. When we announced this on April 10th, we thought that this was pretty cool. And then on April 11th, we came down and we saw this on the front page of every major newspaper on the planet. And then we got worried that we'd started something a little too big. But I think it's just the right size. I think this is the kind of science that speaks to people, that gets people excited, that is a recruitment moment for people at all career stages. And our group is so big that it shows that anybody can start to contribute. And of course, we got the Google animation, which is a special thing. So this has inspired us, and I hope it also inspires you. Thank you. I can't really see.
Do the mass and other properties of the black hole in the center of our galaxy explain how it serves as an organizing principle for the galaxy as a whole, holding everything together?
Yeah, so the question was, well, actually you heard the question. So it turns out that while the black hole is dominant, very close to it, its sphere of influence is actually quite small compared to the scale of the galaxy. So in other words, we have nothing to fear from the 4 million solar mass black holes in the center of the Milky Way galaxy. And now we do, however, feel that black holes of the supermassive variety do evolve in a contemporaneous way with their galaxies through mergers and accretion over long periods of time. So there is some mystery there. How do galaxies evolve with supermassive black holes at their interior? And that's still kind of an open question.
Back here, Shep.
Mm-hmm.
Hi. How big would the black hole have to be, or how massive would it have to be to actually like send the probe inside and not have it get ripped apart by tidal forces before it passes through the event horizon?
Oh, that's a good question. So it turns out that there are two varieties of black holes. One is a stellar mass black hole that occurs during a star death. So after a supernova, you can get a small black hole. The tidal forces at the event horizon there are so great that they would rip just about anything apart when it went through. These supermassive black holes, 6.5 billion, 4.5 million, are so big that you would just sail right through the event horizon without knowing that you were already gone from the universe, right? So there's some middle ground in there where you might start to feel it, but those are the two extremes. So you can have an event horizon where you don't feel it, and then there's definitely an event horizon where you'll be spaghettified.
I have two rotation questions. One
where
is,
are you?
I'm over here.
Okay.
This way.
Gotcha.
First, is the gas rotating or the black hole itself rotating, and does the rotation axis affect your ability to image it?
Oh, wonderful question. So spin. So it's a black. The theorem is that black holes have no hair, right? That a black hole is just a black ball with nothing on it to differentiate what went into it to form it. But there are two basic parameters: mass and spin. So the black hole can spin, and we do think that the M87 black hole, the one I showed you, is spinning, because we do see jets coming out from its north and south pole. But in this case, the gas is circularized around the black hole, and the black hole is spinning. And what we discovered as part of this is that in all the models we use to explain this, even if the accreting gas is moving in the opposite direction as the spin of the black hole, very close to the black hole, it entrains the gas to move with it. So no matter what's happening with the gas around the black hole, the spin of the black hole forces the gas to move with it. And that's what you're seeing. You're seeing the effect of that Doppler shift with the brightness on the bottom and the faintness on the top. That comes from the spin of the black hole. And that's how we know the orientation. But it doesn't necessarily help us image it. We learn that from the very robust image that we made. Does that answer your question?
And you can image a black hole no matter what direction it's rotating?
Yeah, we think so. So it turns out if we're looking at this black hole almost spin axis on. We're almost looking down the throat of the jet coming at us. If we were looking at it edge-on, then one part would be brighter coming on the side, and we'd see more of a crescent. Now, in that case, it might be a little harder to image. We don't know. Our simulations show us that we should be able to image that, but in this case, nature was kind and gave us this black hole in which we were looking at it on the spin axis, so it was fairly well illuminated all the way around.
Shep, back over here and then back over there.
So what are the absorption or loss processes that make, I think you said it was 1 millimeter wavelength, the best one to look at?
So it turns out that in a cosmic traffic jam, all the gas that is attracted towards the event horizon heats up, basically through friction. If you rub your hands together, they'll get hot. It's the same kind of process. And the gas there heats up to billions of degrees. And it's glowing, and that's why we can see it. So you need to be able to look at a wavelength of light that can start deep within the gravity well, near where the strong gravity signatures are born, and it has to make its way through that hot gas. That's the first gauntlet that it has to run. And millimeter wavelengths can do that. A lot of other wavelengths simply cannot. Then it has to go through the galaxy itself, through the M87 galaxy. And there's ionized media there that can scatter photons of different wavelength. Then it has to go through the intergalactic medium, which is pretty tenuous. And then it has to come through the Earth's atmosphere. Okay, so right away it rules out things like infrared, or certain wavelengths of infrared, and also X-rays. And 1 millimeter is kind of the Goldilocks wavelength. That's the wavelength that can make that entire trip, and where most of the energy output of the black hole is coming from in this case. So it's a trifecta, it's a daily double, whatever your favorite analogy is. It's worked out well. And it didn't have to work out that way, but it did.
Yeah. Oh. Yeah. So you used a variety of algorithms in order to process the information and impute data to be able to see these images. Now that you have the image in mind, are you going to continue using all 4 of those algorithms going forward, or are you just going to take your best performing ones in order to be able to up your throughput on processing the data with your future acquisitions?
Yeah, it's a very good question. So I can tell you that right now we're analyzing the data for the Sagittarius A star black hole. It's in the center of our galaxy. And we're employing all the algorithms still as we do that. But more than that, we're expanding the capability of those algorithms. So we're not resting on just those 4. And the reason is that the black hole in the center of our galaxy is 1,000 times less massive. And what that means is that it evolves 1,000 times faster. So an orbit would be half an hour. An orbit of the black hole that I showed you the image of, it takes a month for the matter to move around it. But for Sagittarius A star, during one evening, it moves very quickly. So we don't have the luxury of recording all the data for one evening and merging it together to make a still image. We have to make a movie. It's almost like taking the lens cap off your camera while someone runs by. It's all blurry. So per force, we have to increase the capacity of our algorithms, and we have people working on that now.
I noticed on your map that you're pretty much.
I'm sorry, I couldn't.
I noticed on your map that you're pretty much covering the Western Hemisphere, and there was nothing in China or India. Is that one of the geopolitical constraints you have, or is that by design?
Well, I thought this was a friendly audience. No. Read nothing into that. That's just one potential geometry. And in fact, we are looking now at a very interesting site in India. We've been talking with people all over the world. We want to go to the best places that have some infrastructure where we can fill in optimally this virtual lens. And then wherever that takes us, that's where we'll go. We have some very talented postdocs and students right now working on optimizing where we should go. And they're making heat maps of the entire globe in which we put different attributes like atmosphere, filling factor for the lens, infrastructure. And wherever the white hot pixels are, that's where we're going to go. Any other questions? Thank you.